Hello everybody, so in this video we will be discussing the Otto cycle. In this video we will give a brief description of what the Otto cycle models and give some early applications and just a little brief history about the engine that it models. Let's go into the ideal cycle, which is the Otto cycle, and discuss the differences between the ideal Otto cycle and the actual cycle that the Otto cycle models, and then we'll go into some modifications. So what the Otto cycle models is a four-stroke spark ignition combustion engine. It's the ideal cycle for the cycle that a spark ignition combustion engine operates in. So a spark ignition engine is one of two types of reciprocating engines. And what a reciprocating engine is basically just a piston cylinder. The piston will move up and down in the cylinder and in a reciprocating motion, and that motion will produce energy. I'm going to discuss a brief history about the Otto cycle and how it came to be. So the Otto cycle is named after Nicholas A. Otto, and he was the man who is credited with building the first successful four-stroke internal combustion engine. The development of internal combustion engines began this quest for a more efficient vehicle because up until the combustion engine was utilized, the vehicle designs involved steam engines, which is an external combustion engine. So the working fluid, which is the steam, it's separated from the combustion products, and the steam engine really wasn't very efficient. It had a lot of disadvantages to it. It was very slow to start because you had to boil the water in order for the steam to be produced, and you had to continuously put water into it to keep it running. It was really bulky. It was more practical for large-scale vehicles, but for a personal vehicle like a car, it just wasn't very practical. So this quest began for a more efficient vehicle, and the internal combustion engine was modeled, and then Nicholas A. Otto built the first successful four-stroke. So his invention led to the eventual replacement of steam engines altogether because the spark ignition engine had a much higher thermal efficiency. It was much more compact, which made it more practical for smaller personal vehicles. And one of the huge advantages was that the car would start almost instantaneously. So the spark ignition engine really just changed the game. I'm not really going to go too much into this slide, but if you want to pause the video and read more about it, the main takeaway from this slide is that sometimes in engineering decisions, compromises must be made, and efficiency is only one of the considerations. So in this case of the leaded gasoline, the efficiency had to be compromised in order to benefit the general welfare and the health of the public. So what the Otto cycle models is the four-stroke internal combustion engine, but with the spark ignition engine there are two types, with a four-stroke and the two-stroke. So I will discuss both just to give a little overview of what they are. So the four-stroke internal combustion engine is a reciprocating engine where the piston executes 4 complete strokes and the crankshaft completes 2 revolutions. So in the four-stroke, there's a compression stroke, power stroke, exhaust stroke, and intake stroke, which I will show a visual to make a little bit more sense. But in a two-stroke engine, all 4 of those functions are only executed in 2 strokes. So the two-stroke engine only has a power and compression stroke, but it does everything that a four-stroke engine does just in 2 strokes. However, the two-stroke engines are less efficient. They lack the maneuverability that the four-stroke engines have, but they do have high power to weight and power to volume ratios, so they are rather appropriate for smaller devices. So a four-stroke spark ignition engine, which is what the Otto cycle models, is shown in this schematic. So there's an intake stroke where the air-fuel mixture comes in and the volume increases, and this produces half of a rotation of the crankshaft. And then another half rotation of the crankshaft occurs in the compression stroke, which is when the piston moves up and compresses, and then a spark is introduced, igniting the air-fuel mixture. The piston goes down, and another half rotation occurs, and this is known as the power stroke. And then another half rotation, so 2 full happens at this stage. The piston moves back up, expels the exhaust products, and then the whole cycle continues again. So this is what the Otto cycle models. This is a animation that might make a little bit more sense. So this will just show this is the intake, compression, power, exhaust, and it just continues to happen. You can see the crankshaft rotating and how this is occurring. So yeah, but then for the two-stroke, the intake and the compression occur in the same and then the power and the exhaust occur in the same stroke. So a four-stroke gasoline engine is the engine that is involved in almost all cars, also in some small trucks, but in more larger scale trucks, the diesel engine is utilized. But then a two-stroke gasoline engine is often involved in smaller devices, as I stated earlier. So they're often in motorcycles, and they're the engines always used in lawnmowers and chainsaws.
In this section, we'll be talking about the ideal cycle of an Otto cycle. And so for analysis purposes, we're going to simplify a real-world version of the Otto cycle, and we're going to model it as a closed system made up of entirely reversible processes. For a four-stroke Otto cycle, we have exactly four steps, I guess you could call them. But we do have this 0 to 1 step, which is the intake stroke, but we're going to mainly focus on 1 through 4. So starting at point 1, we'll have the piston head at bottom dead center, as you can see here on the diagram. And then from 1 to 2, we'll have isentropic compression. So the volume changes at this point, and you can see at position 2, the piston head will be at top dead center. So from 2 to 3, we'll model this as heat addition into the system. Normally this would be the internal combustion point, but for analysis purposes, we're going to model that as heat into the closed system. So at 3, we're still at top dead center, and so from 3 to 4, we'll have isentropic expansion. As you can see, the volume increases, and so then 4, the piston head is back at bottom dead center. So from 4 to 1, though, we'll model this as heat out of the system. To get back to 1, we'll model as heat out of the system. Normally this would be the exhaust stroke, but for this purpose, it's heat out of the system. And then for this slide, we have a TS diagram of an ideal cycle. And if you remember at point 1, we're at bottom dead center. And then from point 1 to 2, we're at top dead center at point 2. So the volume is changing here, but it's isentropic, so the entropy stays the same, and that is reflected in the vertical line here. You can see the same thing from 3 to 4. The volume is changing, but the entropy is staying the same, so we'll have a vertical line here from 3 to 4. And then from 2 to 3 and 4 to 1, we have constant volume, but the temperature changes because we're going to model it as heat addition and heat removal from the system. And then if we were going to speak of the ideal Otto cycle in terms of the first law, if you remember, the first law is Q minus W equals delta U plus delta KE plus delta PE. And in this case, we can ignore kinetic energy and potential energy for all cases because macroscopically, the ideal cycle is not moving. I know there's boundary work, but macroscopically there's no kinetic energy and potential energy. So we're left with Q minus W equals delta U. And then from 1 to 2 and here 3 to 4, Q equals 0 because there is no heat removal or heat addition. So we're left with work. Work equals delta U. And from 1 to 2, we're having work into the system because for that compression stroke. And then here, the power stroke, we have heat going out of the system. So we'll have the WB positive. For 2 to 3, there is no work because the volume stays the same. And since the volume stays the same, the work will go away. So we're left with Q equals delta U. And in this case, it's positive. From 2 to 3, it's positive because there's heat going into the system. And then here, it's going to be negative because there's heat going out of the system. Just so you can see visually what it looks like, we'll go over it one more time. Starting at position 1, bottom dead center here, you can see the piston head is at bottom dead center. And then from 1 to 2, we'll have that isentropic compression here. And then at 2, we'll be at top dead center. And then we'll have that heat transfer in from 2 to 3, heat transfer while the volume is staying constant. So at 3, we're back at top dead center. And then from 3 to 4, we'll have isentropic expansion. The volume is changing here. And so then we're back at bottom dead center. And to get us all the way back to position 1, or point 1, not position 1, point 1, we'll have that heat removal out, which would normally be the exhaust stroke, but it's the heat removal out. So then we're back at 1 after we have that heat removal.
I'm going to talk about actual Otto cycle. Thanks to Paris and Malach, four-stroke and processes of Otto cycle was introduced. So I will focus on how the actual Otto cycle is made and what factors are contributed to the actual cycle. Before we start, I'm going to go over differences actual cycle and ideal cycle. Ideal cycle is basically under air standard assumptions. Working fluid is air in a closed loop, so fluid can be treated as an ideal gas. All processes are internally reversible. However, air and fuel mixture goes into cylinders on the actual cycle. In this actual cycle is open system. Also, there are many irreversibilities on the actual cycle. Let's go back to the air standard assumptions. Combustion is replaced with a heat addition process, but combustion is conducted in real world. This contributes to taking time to combust air-fuel mixture, which means not instantaneous heat addition, and incomplete combustion due to possibility of lack of oxygen in cylinders. The rest of these three losses, blowdown loss, pumping work, frictional loss, is going to be explained on the later slides. These are a list of loss sources: heat transfer, combustion loss, exhaust blowdown loss, Kravitz effects and leakage, pumping loss, and frictional loss. Kravitz effect is that fuel enters the gap or crack inside the cylinder, so all fuel is not burned and fuel leakage can occur. Frictional loss indicates the friction of the piston cylinder or the crankshaft connected to it. So the first factor is heat transfer loss. Basically, actual cycle is not a closed and adiabatic system. The outer line is ideal cycle. Yellow shaded area is lost due to the heat transfer loss. Heat transfer from the burned mixture to the cylinder walls. And cooling by coolant is also effective to prevent overheating of the engine. Therefore, heat in the cylinder transfer to the coolant. There are two main factors due to the combustion time and incomplete combustion. Right side of the graph, x-axis is crank position and angle. If the piston is located to the top dead center, it is 0-degree position. If the piston is located on bottom dead center, it is 180-degree position. I'm going to focus on this area, combustion area. Combustion typically starts 10 to 40 crank angle degrees before TC, which is top center, and is essentially complete 30 to 40 after TC. Peak pressure occurs at about 13 to 15 after TC. The peak pressure inside the cylinder is lower than the ideal cycle because combustion is not completed instantaneously. And the other factor is incomplete combustion occurs when the supply of air or oxygen is poor. The lack of oxygen does not completely burn all the fuel, so it does not produce the expected efficiency. So this green area is lost due to the combustion. The next factor is blowdown loss. What is the blowdown? The exhaust blowdown is that the combustion gases that are above the atmospheric pressure rush out of the cylinder through the open exhaust valve when the exhaust valve opens. This blue shaded area is lost due to exhaust blowdown loss. The blowdown loss occurs when the high pressure gas exhausts after the combustion. The next factor is pumping loss. Pumping loss occurs due to that the difference between cylinder internal pressure and external pressure during intake or exhaust causes heat loss through intake or exhaust valve. So this pink shaded area is lost due to the pumping. So we started this graph. If the loss area is erased, it is very similar to the textbook PV diagram. For the round corners, the valve does not open and close instantaneously, so the loss on that part makes the corners round. Actual engine cylinder has spark ignition tool and valves which make air in and out of the cylinder. So here is actual Otto cycle TS diagrams. Normal line is for ideal and dashed line is actual cycle. The ideal Otto cycle is swinging to the right due to the irreversibility. Change of entropy is equal to integral of dq over t plus Sgen. Despite of air standard assumption, entropy change occurs due to the Sgen value, which is 0 or always positive value.
Let's go over two modifications that are made to the Otto cycle and their real-world applications, starting with the hypergolic engine. Hypergolic means that ignition occurs when two substances are mixed. In this case, for the lunar rover that uses the hypergolic engine, N2H4, which is hydrazine, is mixed with dinitrogen tetroxide, N2O4, to create the ignition process. The hypergolic engine has the benefit of not requiring a outside ignition source such as spark plugs, and therefore is more reliable over longer periods of time where a breakdown would be catastrophic, such as exploring the surface of the moon. This cycle is modeled as an Otto cycle, specifically a two-stroke Otto cycle, with CO2, with a constant volume on either side, adiabatic expansion, and adiabatic compression. Similar also to an Otto cycle, the ignition occurs at top dead center within the stroke. This diagram specifically also has the ideal cycle compared with the actual cycle, showing that there would be loss from combustion leakage, compression, and the porting of exhaust. In this cycle, fuel and oxidizer are mixed in the engine, with waste heat being pumped as thermal energy for the life support systems to overall increase the energy being used and to reduce the amount that is waste when it is ported out as exhaust. This system does not come without its problems. The fuel and oxidizer are both stored in liquid form before injection, which requires them to be kept at a temperature between 20 and 140 degrees. Through what is called super insulation, when these tanks are full, the requirements on the temperature aren't an issue and is naturally maintained. However, as these tanks begin to empty, some of the work has to be diverted to the tanks to maintain their temperature through temperature control units, reducing the overall efficiency. Other issues of this include that the hydrazine is both corrosive and toxic, making it difficult to handle, and all of the parts have to be treated so that it doesn't damage them over extended use. Another application of the Otto cycle was the development of the Atkinson cycle, which is so similar to the Otto cycle, is often called the extended Otto cycle. While the Otto cycle uses two constant volume processes on either side, the Atkinson cycle swaps the 4-to-1 constant volume process with a constant pressure process. During this, the expansion stroke is lengthened first by opening the inlet valve during the expansion stroke, allowing for a relatively smaller compression ratio or lower maximum volume than the regular Otto cycle, but the full force of the piston being pulled down is utilized instead of being ejected as waste when the exhaust is opened. These graphs are slightly inaccurate. The Otto cycle creates an overall larger amount of work compared to the Atkinson cycle. So the 4 prime, this box represents a actually larger area than the box of the 4, which is the Atkinson cycle. Due to the lower compression ratio and lower area between the curves, the Atkinson cycle actually has a smaller amount of work generated per cycle, but because it utilizes more force of the piston and rejects less waste heat, it actually has overall higher efficiency. Now, in order to best utilize this, most hybrid cars use variable valve timing, which swaps between an Otto cycle and an Atkinson cycle when it is most needed. At times where a lot of power is needed, it will use an Otto cycle, and at times where it needs to run efficiently, it will run the Atkinson cycle. And that's everything.